Okay. So last time, so since I was running out of time, so I was not able to finish the discussion. So let me remind you that last time, we tried to compute these two improper integrals. Well, precisely speaking, so we wanted to compute the Cauchy's principal values of these two improper integrals, and we were assuming that f of x was a rational function, so which is nothing but a quotient of two polynomials satisfying these three conditions. And it turned out, in this case, the Cauchy's principal value of this guy was the real part of the summation of all these residues. And this guy is the imaginary part of this. Okay, all right. So let me quickly turn to the example of this theory. Well, this time I want to compute cosine 2x times over x squared plus 4 squared and dx. I want to compute this guy. First, I want you to notice that this integrand function, which is an even function, right? So therefore, if you try to integrate this guy from minus infinity to plus infinity, then the Cauchy's principal value of this number will be the same as just regular improper integral, right? So what we're going to do is we will try to find the Cauchy's principal value of this guy from minus infinity to positive infinity, and we divide it by 2. Okay. Okay. So well, in this case, my function f of z is 1 over should be z squared plus 4, everything squared. And above the x-axis, I can see just one singularity, which is 2 times I. So I have here 2 times I, and this is the pole of order 2. Okay, so f of z, so therefore, so ES, so we want to compute, well, this time around, but our number parameter S should be 2, right? So I just say e to the 2 times I times z. So this guy also has a pole of order 2 at this point. So let me try to compute the residue. Okay, since this is the pole of order 2, so should be 1 over 2 minus 1 factorial times the limit z is tending to 2i and so I should be multiplying everything by z minus 2 times I squared times f of z times e to the 2 times iz. And taking derivative, how many times? 2 minus 1 times. So this is the first derivative. So what is this? So this is the z is tending to I. So this is just 2e to the 2 iz over z plus 2i everything squared. And taken derivative, right? Okay. Well, now this is just a matter of computation. So, well, we apply the quotient law. So z to the z plus 2i to the 4th and 2 times I times e to the 2iz times z plus 2i squared minus 2 times z plus 2i times the exponential of I 2 times I times z. And all we need to do is just plug in z equals to 2i, right? Yeah, this is just a tedious computation. So, well, actually, last night I did this computation by myself, which that turns out to be 5 times I everything by 32 to the e to the fourth. So, well, so minus infinity to infinity. So f of x times, well, I should better say it. Well, cosine 2x over x squared plus, was it 4? Yeah. 4 squared should be the real part of, so this is the only my own one and only residue. So we are taking the real part of 2 pi I times this residue. And this is what? So this is just 10 pi over 32 times e to the fourth. Okay, so. Okay, good. So therefore, our answer is from 0 to infinity and 5 pi over 8 times e to the fourth. No. 32. Okay, great. All right. Okay, great. And we have a couple of more examples for this residue integration. Well, and today we also want to discuss about another kind of improper integral. So, well, the first kind, well, when we were in the single variable calculus course, so we have been discussing so we already know there are two types of improper integrals. The first type of improper integral is the integrand is bounded, but the interval is unbounded. So, well, so most of the time, so we say this is the improper integral of type 1. But there is another improper integral, which we sometimes call it improper integral of type 2, which is about this. So the interval is now bounded, but the integrand function is unbounded. Well, in this case, we say that it's an improper integral. And this residue integral can be also applied to these improper integrals of type 2. So another kind of improper integral. Well, let me assume this function. I have a function which is defined almost everywhere but a point A, and which looks like this. So this is the point that x equals to A, and my function behaves like this. And this is point, well, I say this point is A, and this point is B. And the question is, I want to integrate this guy from interval A to B. Well, so do you remember the condition that this improper integral of type 2 exists? So, well, in order to see that, we actually need to break down this integral into two different pieces. Which is, the first one is A plus A minus epsilon. And the another one is A plus, well, eta and dx. And this should be tending to 0. And so this improper integral is defined by these two, right? And so I want you to recognize that I have two independent parameters, epsilon and eta, and as these two independent parameters tending to 0, independent from each other, then if these two limits exist, then we can at last then we can say this improper integral exists. So in other words, shortly speaking, so this guy exists if and only if this guy and this guy both exist. But there is a so-called a Cauchy's principal value of improper integral of type 2. Is defined by defined by this. So can you see the difference between these two? Yeah. So here we have two independent variables, epsilon and eta. But in this case, well, these two variables are the same thing. So therefore as epsilon goes to 0, and if this integral exists, then we say the Cauchy's principal value of this improper integral also exists. Okay, so therefore, if an improper integral exists, if this guy, in traditional sense, if this guy exists, then this one also exists, right? But the other way around, which is generally not true. Okay. And today we want to compute. What I want to compute is not this guy, but this guy, the Cauchy's principal value. Well, usually this Cauchy's principal value, the existence of the Cauchy's principal value does not guarantee the existence of the traditional improper integral. But suppose that my integrand function is an even function, then the existence of Cauchy's principal value will now guarantee the existence of the improper integral. Okay. Now suppose that my function f of z has a simple pole, the pole of order 1, at this point. This is a point on the real line. And I want to define a curve which is a semicircle. The upper half of a circle z minus a is r. And generally, so we assume that this r is very small number. And I want this guy to be oriented counterclockwise. So like this. So, well, my function, this is a real line. This is a point on the real line, which is A. And I have a circle. Well, this is semicircle. So this is A plus R, and this is A minus R, and this is oriented counterclockwise. Okay, so this is my C of R. Now, what I want to do is I want to consider the path integral, the line integral of this guy along this curve. And in order to do that, first I will need to have a parameterization of this guy, this curve. So the one most obvious parameterization of this guy should be a plus r times e to the I times t, and t is from 0 to pi. So this is a parameterization. Okay. And before we try to integrate this guy, I want to find the Lorentz series of this function around this point. Then, well, this is the first negative coefficient, and z minus a, and plus some analytic part. So I'm not interested about this, so I'll just say g of z. And let this guy be a, not a, actually, the Lorentz expansion of f about a. So therefore, since we are assuming that we have a simple pole at this point, so this is my one and only negative exponent of z minus a, and this is then this guy is going to be my residue. And I want to integrate. If I integrate my function along the curve CR, then I can break down this integral into these two, z minus a dz plus CR of g of z dz. Okay, and I want to tend my parameter, the radius of the circle r. I want this guy to be 0. I want to set this guy to be 0. And in order to do that, first I want to see that this number should be also tending to 0. How can I show that? Oh, great, right. Well, since this is the analytic part of this function, so this guy only consisting of the positive exponent of z minus a. Therefore, clearly this guy is an analytic, and which also implies that this function also be continuous. So since g of z is analytic, so this is continuous. So there is some positive integer such that the modulus of g is bounded by m, and here I want my z to be so what do I mean by this? So here I require my z to be every point that is bounded by these two. Okay. Okay, so well, clearly this is a closed and bounded region. So well, I must be able to find a positive integer satisfying this. Okay, so no. And what is this? This is just nothing but b1 times 2 pi, not 2 pi times I. Right? Sorry. So if this guy were a full circle, then this one should be 2 pi times I. But this is just a half circle. So this is just pi times I, which is very obvious. And for this guy, and I want to consider the modulus of this guy. So this is CR G of Z dz. And here again using the ML inequality. So this integrand is bounded by M, and the length of curve is pi times R, right? So as R is tending to 0, we know that this guy, with the modulus of this guy should be tending to 0. Therefore, this number also should be tending to 0. So as R to 0, is pi times I times the residue of f of z. Okay. Correct. All right. And this idea, and this actually gives some idea how to compute the Cauchy's principal value of some function which has a simple torr at z equals to a. And I have very important application of this theorem. And I want to introduce just one more lemma before I show you the important theory. I have a function f of z is analytic in the upper half plane outside of well, I have a circle. And this is the origin. And we require that my function is analytic on this region. This is and the condition number 2 is let CR be a semicircle right, beta. So what is this? So this semicircle, CR, is a circle that is contained in this green region. So this is CR, and the radius of this semicircle is slightly bigger than this R0, this number, R0. And we are assuming that on this circle, there is a positive constant such that f of z is bounded by mr. And on top of that, we are also assuming that this number, this bounding number, m sub r, is tending to 0 as r to the infinity. Well, so lots of conditions. And under this hypothesis, and for all possible constant a, tending to 0. Okay, so what a technical lemma. Okay, all right. So let me prove this. This lemma is sometimes called the Jordan's lemma. Okay, whatever it is. So first, I want to claim that well, for any positive real number R, and we have this inequality. So this is actually the inequality on the real integral. So this is not a complex integral. This is a real integral. Why is it true? Let me say this is a curve y equals to sine theta. And this is, well, the x coordinate here is just obviously pi over 2. And I want to compare and this is a curve that y is 2 over pi times theta. And just let me just focus on the case when the theta is between 0 and pi over 2. And on this closed interval, clearly this guy is above this line segment, right? So sine theta is bigger than 2 theta over pi here. Okay, so this guy is bigger than this, and so minus r times sine theta is less than r times 2 theta over pi. So since exponential is an increasing function, e to the r sine theta is bounded by e to the r times 2r theta, everything by pi. Okay, all right. And so therefore, if you integrate these functions from 0 to pi, it's pi over 2. And this is 2r theta over pi d theta. And this is what? This is just pi over 2r and 1 minus e minus r. Okay. Yeah, great. And clearly, since r is a positive number, so this number should be some number between 1 and 0. Therefore, this number is bounded by 2r, right? Okay. And on the other hand, I want to use a little change of variables. I'm going to define another variable, namely phi, which is defined by theta is pi minus phi. So in this case, so this is 0, and this is pi over 2, and e to the r sine pi minus phi and minus d phi. And so r phi, sine of pi minus phi is just same as the sine of phi. So simplifying everything, so it turns out this is E minus R sine phi d phi. Oh, okay, but just forget about the phi. Yeah, I will just say this is theta. Oh, so surprisingly, this one is the same as this guy. And we already know that this guy is also bounded by pi over 2 times r. So combining these two results, well, if I add this guy, this integral to this one, and by the summation law, so this integral is now the integral of this function from 0 to pi, and this is bounded by, well, yeah, pi over r, right? Okay, great. Okay, so we now prove this inequality. Then, okay, what am I supposed to prove? Okay, so yeah, I am supposed to prove that this guy is tending to 0. So the CR of f of z e I a z dz is what? So because of my parameterization of the circle CR, so f of r times e to the I theta times, well, I will just say exponential I times a times r times e I theta times, well, dz is just simply r times I times e I theta, then everything d theta. Okay, and you know what? This number, well, this is a point on the circle CR, and we already know that this number is bounded by m sub r, so which is given by this hypothesis here. So this is bounded by mr times, and also this r is now out of the integral, and from 0 to pi of exp I a r e I theta. And well, the modulus of this guy is just 1, so I can simply ignore this. So, well, we have this inequality. And what is this? So this is I times a times r times cosine theta plus I sine theta. And since we are talking about its modulus, so therefore the imaginary part of this guy doesn't matter. So is just mr r times from 0 to pi and e to the, well, I have twice, minus a times r times sine theta, everything by d theta. All right, yeah. Okay, so can I make use of this theory? No, so not exactly. Because I have a here, but I do not have a there. Well, but this problem can be simply resolved by using a simple change of variables. So this is mr times r, yeah, sorry, is bounded by, this is bounded by pi r, and so I will need to put one additional number a over here. Yeah, good. So mr pi times mr over some positive number a. Okay, now as r tending to infinity, and since this guy is also tending to 0, right? So therefore, if as r tending to infinity, then this guy is tending to 0. Therefore, so this weird integral is tending to 0 as r to the infinity. Okay. Wow. All right. Okay. Now we are fully ready. Now it's time to introduce the biggest theorem in today's lecture, which is called the Dirichlet's integral. Well, just imagine that we are not in the complex analysis, but we are a student in the freshman calculus. So, well, you know the Maclaurin series of this guy, right? And if you divide this Maclaurin series by x, then you're going to still get some nicely converging power series, right? So this number is clearly bounded in this interval. So you might somehow expect this improper integral. And it turns out this number equals to pi over 2. So how we can get this number? Well, but unfortunately, the antiderivative of this guy is known to cannot be written as a combination of the elementary functions. So not a good news. So we can actually compute this guy by using the theories that we discussed so far. Well, actually, frankly speaking, so there's another way around, so-called the Feynman integral transform. You're not talking about that. All right. Well, now we consider sorry, not SC. We want to consider this function, exponential divided by z. And what is my so where is my singularity? So there is only one singularity, which is a simple form located at the origin, right? So this is my singularity, and I want to consider this curve. No. And another circle that looks like this. Well, these two semicircles, they are all centered at the origin, and the radius of the first one is small r, and the radius of the second is large r. And I want to consider this contour, or this curve, this closed curve. Well, first, I traversed along this curve CR in this counterclockwise direction. And at this point, I will travel along this straight line segment, then this, and like that. So this is a very nice closed curve. And the nice news is that this closed curve is actually does not enclose any singularity of the viewer function, right? Well, for simplicity, I'm gonna call this first straight line segment to be L1, and this is L2. Then, you know what? The integral of this function and L1, L2, and CR and CR. These guys equals to Z, right? Because, well, there is no singularities inside. Well, first I want to discuss about so this is from R to R, and this is minus R, and this is minus R. So, well, this is a integral on the real line, so this guy should coincide with the integral on the real numbers. So from minus R to minus R, and e to the it over t and dt. Well, I don't like having the negative signs here, so by changing of variables, I'll say this is R and R, e minus it, and minus it, minus t, and minus dt. And so yeah, just simply just t dt. And well, also I want the larger guy on the top and smaller guy on the bottom. So large R, small r, e to the I times t over t and dt, and with minus sign. Okay. So this is what? So the integral of this guy along this line segment is just e to the it over t and dt. And this one is known to be this guy. So this is R to R, EIT minus e to the minus IT, everything over t. Hold on. So this one reminds me of some trig function. So what trig function? So if I divide by 2 times I and multiply by 2 times I, and also everything dt, then this is 2 times I times the sine of t, everything divided by t, okay, and dt. Yeah, this is also very interesting because, well, now this number coincides to this integrand function. And if I send r to infinity and small r to 0, then this number will be tending to this Dirichlet's integrals. Okay, so I want to set my r to 0 of CR of f of z dz. This is EI z over z. And, this is a simple pole, which is a pole of order 1. And okay, now I go back to the previous lecture note. And it says, if my function f of z has a simple pole as some real number, then this limit will be tending to pi times I times the residue of this point at this point. Okay, but yeah, hold on. So, but this time around, this guy is now oriented counterclockwise, but now my curve is oriented clockwise. So yeah, so therefore, this guy should be minus pi times I times the residue. And what is the residue of this point? So z0, so which is just 1, okay? So minus pi times that. And what about the another semicircle? As r to the infinity, this is EIZ over Z, dz. Okay, now this is time to make use of the previous lemma. In this case, we should consider our function is just 1 over z. And 1 over z is, well, obviously analytic on this green region. And also we can find this number, m sub r, which is just 1 over r, right? Then, so on this circle, my function, the modulus of my function is bounded by 1 over r. And, well, clearly 1 over r is tending to 0 as r goes to infinity. So therefore, this integral should be 0, right? Okay. All right. So, okay, so as small r goes to 0 and large r goes to infinity, and this guy, and well, this guy is tending to minus pi times I, and this guy is tending to 0. And sum of these two integrals can be written like this. So eventually, this one is, well, pi times I. So, oh, sorry. This time around, so this is 0 to infinity. And so 0 to infinity of sine x dx is just pi over 2. Okay. So this integral was known to be very important, but previously they were able to prove that this integral somehow exists. Well, this guy is known to be convergent, but they have no idea which number this integral is convergent to. But with the help of the residue integration, so we finally know the answer, which is tending to very beautiful number, pi over 2. I believe this is one of the most important breakthrough that was found given in from the residue integration. All right. Okay. So, well, yeah, I know this is getting a little bit tedious, but well, I have 2 more important examples. So let me try to introduce these 2. We are supposed to show that this example itself is not important. But however, the trick that I am using is important. A pi by 2. And my parameter A is a number between -1 to 3. Okay. All right. Okay. All right. Okay. So well, since we are in the section of the residue integration, so I feel like I will need to apply some trick on the residue integration. So maybe this is a huge maybe, but I want to set my function f of z to be z to the a over z squared plus 1 everything squared. But you know what? In this case, we are talking about a complex number raised to some positive real power. So basically, we need to introduce the exponential composed with the logarithmic function. And speaking of the logarithmic functions, we should be considering the branch of this function. But which branch? Okay, this is very important question. So I say this numerator is a times ln of z over this. Okay, so okay. For now, let me just ignore the numerator. And for the denominator, so well, I can see a 0 of order 2 on when z equals to I, right? So, and also, you also need to notice and realize that this logarithmic function, no matter which branch you choose, this function is not well defined at this point, right? So maybe I will need to consider this guy on the top and this guy inside. So, well, as before, this is CR, and this is C small r, and this is L1 and L2. Okay, so I want to consider the integration of this function about this contour, and the best branch for this contour should be my branch curve should be somehow looks like this. Okay. If I put my branch along the negative y-axis, then this area of integration does not contain any of these branch points. So here I say, oh sorry, z is positive, and I require that my argument from minus pi over 2 to 3 times pi over 2. Okay. So this is my branch. Okay. So the CR plus CR plus L1, L2 is just 2 pi I times the residue of Z is 2I of okay, well, this is just tedious computation. So I already computed the residue for you. So it turns out that this entire thing is 2 pi I times, well, provided that my computation is correct, e to the I pi over 2, 1 minus a pi. Okay. Okay, so you know how to do this, right? So therefore, since this is the total of order 2, so in order to do this, we are supposed to multiply everything by z minus I squared. So then my function is going to be a ln of z, the z plus I squared, and we take an integration. Then this is just then this is z plus I, everything to the fourth, and so this is z to the a. So a times z a minus 1, z plus what I squared minus z a and z plus I 2 times, and you evaluate when z equals I. Okay, so Well, but you know how to, so you know how to deal with when I is raised to the power of a minus 1, okay? Because since the argument was clearly stated here, so, well, I guess you will have no trouble in computation of this guy, okay? Which I will leave it as an exercise. All right, okay. So, okay, residue is done. Now, on this larger semicircle, CR, Z of A, the modulus of this number is, well, clearly exponential of A times ln of Z. But this is ln of, well, when my point is on this semicircle, then this is going to be ln R times I times theta. But, well, this imaginary part has no effect in computation of the modulus. So therefore, I feel like this is the R to the A, I think. Yeah. And also, well, denominator, which is Z squared plus 1, is when Z is large, when the modulus of Z is large enough, then we have this inequality. So this is bounded by R squared minus 1. Okay, so the modulus here, CR ZA Z squared plus 1 squared dz is bounded by R to the A's by R squared minus 1, everything squared, times the length of curve, which is pi times R. And so, okay. Now I want to show that this guy tends to 0 as R to the infinity. Hold on. So what was my range of the parameter A? So A was between -1 to 3. So for the worst possible case scenario, when A equals to, well, A is very close to 3, then the degree on the top is 4, slightly less than 4, and degree on the bottom is precisely 4. Yeah. So I'm sure that this guy tends to 0. Okay. All right. Now, for the smaller semicircle, the same thing is true. ZA is just small r to the A, and Z squared plus 1. But now this is, well, but in this case, CR, the radius of R is assumed to be very small. So obviously, this number it should be smaller than most cases, smaller than 1. So this guy is bounded by 1 minus Z squared. So is bounded 1 minus small r squared. So CR ZA and Z squared plus 1 and DZ is now bounded by R to the A over 1 minus R everything squared. Now I want to show that this guy tends to 0 as R tends to 0. Yeah, this is clear, right? Oh, sorry. I forgot to multiply by the length of the curve, which is pi times R. Okay. But anyway, this guy tends to 0 as R to 0. Okay. All right. So now we are done about these two integrals. And now we should be talking about these two integrations. This integral along this line L1, which is from minus R to minus R. So So L1 f of z dz is just a from minus r to minus r. Sorry. Just exp a ln z over z squared plus 1, everything squared, and we are, well, setting t is from minus r to minus r. So minus r to r, and exp of a times, what is the ln of this guy? Well, here, so my z of t lies in the negative real axis, right? So I mean, so my point z is somewhere around here. Therefore, the argument of this number is, well, actually pi, right? So a times absolute value of t plus I times a times pi. And okay, so this is t squared plus 1, everything squared, and dt. So this is from here, I have absolute value of t to the a times e to the I times a times pi, and t squared plus 1, everything squared dt. Well, again, by changing of variables, so this is r, so this guy just carries over. And everything squared, so sign doesn't matter for the denominator, and minus dt. So, oh, sorry. Okay, so this is e to the ia pi from r to r, and okay, well, now here we are talking about the t's between plus r to plus r. So, well, I don't need to take these negative signs, so absolute value signs anymore. Okay. And, well, considering, so this is the integration on this negative real axis, and for the positive real axis, L2 f of z dz is, this is easy. This is just simply from r to r, but in this case, when your number is on this positive real axis, the argument here should be 0. So, well, all the computation just carries over, but this time around, so you won't see any of these factors at all, right? So this is just t times a over t squared plus 1, everything squared, and dt. So, so integral from L1 to L2 is just 1 plus e to the I times a pi from r to r. Yeah, I'll just say x. X squared plus 1 square and dx. Okay. All right. Okay, so now what I want to do is I want to set r to positive infinity and small r to negative infinity. Then we know that this guy tends to 0 and this guy also tends to 0. Therefore, this entire thing, so this guy is 0, this guy is 0, and this guy equals to this number, right? Okay. So is but okay. All right. So, and you solve this equation and equate for this integration. And it turns out that this number is pi over 4 times 1 minus a times 2 over e to the minus ia pi over 2 plus e to the ia pi over 2. But using simple algebra, well, this guy somehow looks like some trig functions. So, well, just do with little help from the algebra. So you now know that this is just 1 over cosine a pi everything by 2. Okay. Wow. So this is this. Okay, so yeah, I say this is not easy. Yeah, this requires a lot of computation, a lot of practice. So, well, this is just a quick reminder. So, on this semester, yeah, I am supposed to make a problem for the graduation examination for the math major student, and especially on the complex analysis. And all these problems were. And so I saw the problems from the previous years, and all these problems were related to this technique. Okay. All right. Anyway, so this is basically the idea. So just one more exercise, but I know you're getting a little bit tedious and tired. So yeah, I'm not going to show you the full detail of this last exercise. I'm just going to give you provide the idea. I want to integrate this improper. I want to evaluate this improper integral. Okay. All right. So, well, so I feel like to define my function f of z to be z to the negative eighth power a by z plus 1. Okay. Okay, so now I want to locate all of these singularities. And I have just only one singularity at this point, right? So here. So this is my singularity. And well, I feel like also I want to evaluate this improper integral with the help of the residue integration. But the problem is, well, this is the problem. So again, so we need to deal with complex number exponentials, right? So therefore, inevitably, we will need to introduce the we need to introduce some branch of the natural log function. So what branch do you want to take in this case, in this very special? Well, there are many choices. Well, you can actually choose your branch to be from starting here and go to here and starting from go to there. But in this case, I will need to choose, I want to take my branch to be this positive real axis. Then, so this is the exponential of minus a of ln of z. So here, argument of z is from 0 to 2 pi. And now this is some crazy idea. I want to consider this. So this is this larger circle is CR, and I go here, and this is L1. This is C small r, and this is L2. So this is my closed, but this is my closed curve, and this is where my singularity is. Okay, so what you're supposed to do is this: you evaluate. So well, so you know well this guy, this number L2. So these two line segment L1 and L2. These two guys are very these two guys are very close to the real lines. So well, you can actually consider this is the same as almost the same as the integral of this curve along this real axis, right? But so you have to be careful because since we are dealing with so well, the point and this point has the argument which is very close to zero, right? But anyway, but on the other hand, the point on this line segment whose argument is now very close to 2 pi, right? So this is something you will need to consider. So, and also the second, and also you will need to see that this integral around this curve is tending to 0 as r to the infinity, and this guy is tending to 0 as r goes to 0, right? So therefore, CR plus CR L1 and L2 is the 2 pi I times residue of my function. And these two guys tend to 0. And you can actually so this one, L1 is from times e to the I times well, because well, this since we are traveling in we are traveling in this direction, so this is from minus infinity to plus infinity, and I will need to 2 IA pi times of this plus, and the another one is x minus a over x plus a dx. So you're gonna end up with this in computation, which I will leave it as this guy is this equals to this, and this guy equals to that. Well, these two guys, they are slightly different. Actually, we have this vector for this one because why? Because since we are working on this curve L1, and every point is argument has the argument 2, which is very close to 2 pi. So this is the reason that why you are supposed to have this vector for this. And also, lastly, I don't think so. I think this is you have no trouble in computation in this residue. And if you're taking the proper limit, then you will get the answer. Okay. So this is how you deal with the improper integrals, especially when you have some exponential functions. Okay. All right. Great. Yeah. So I believe my lectures are usually very tedious, but today's lecture is especially more tedious. And I also strongly appreciate your patience, and see you next time. Okay.